Welcome. We're going to go ahead and have a little bit of fun together today. I have 4 ASR 1000s in the other room in my lab environment at work, and I have 2 4948s. The 4948s are R1 and R2. They are going to be customer routers. We're actually going to put them in VERPs, so Charlie6 actually has a physical interface. That physical interface that connects to R1 is in a VERP. It's called customer A. And Charlie17 also has a physical interface that's connected to R2 in a VRF, and that is also connected to customer A. We call them VRF customer A's. It really gets into RDs, RTs, route targets, and route descriptors, and things like that. We're not going to get into that stuff today. What we're going to get into today with MPLS L3VPNs is we're going to go ahead and do some label following fun with fish. So RTs, VRFs, RDs, things like that we're not going to talk about. We're going to follow the labels so that when router 1 tries to ping 10.100.100.2 over on router 2, how do the multi-protocol labels get switched? How do they come up with them? How does 10.100.100.1 and 10.100.100.2 actually ping each other? Let's talk about that. From R1 and R2's perspective, they don't really know or care that there's all of these routers in the middle. If we actually go over to R1 and we do a show IP route and include 10.100.100.2, what we'll see is that R1 thinks that it has learned via BGP from 10.1.6.6, its BGP neighbor on that LAN, on that physical interface. It has learned how to get to 10.100.100.2. Same thing as far as R2 is concerned. Show IP route, include 10.100.100.1, same thing. So R2 thinks that it can just go ahead and go to 10.17.2.17, which is its eBGP directly connected peer, and get there. And so I just go ahead and I do a ping 10.100.100.2, and I source it from 10.100.100.1, and it goes ahead and gets there. Now here's the interesting thing. As I was mentioning, this is not what it looks like. It actually looks like this. So if we go over to Charlie6 and we say show IP route include 10.100.100.2, Charlie6, who is, as soon as R1 pings, Charlie6 doesn't know how to get there. And that is, of course, because we have VRF'd it off. So Charlie6's connection to Charlie7 is in the global routing table. Charlie6's connection to R1 is in a VRF. If we actually do a show VRF, we will see that we have one that has a customer name of A, and it's actually connected on gigabit 000. If we do a show run interface gigabit 000, we will see that it's 10.1.6.6. All of these IP addresses are, by the way, 10 network. The second octet is the router on the left. The third octet is the router on the right. And the fourth octet is the router ID itself. So Charlie6 would have a fourth octet of .6 on all of its physical interfaces. So what you can see here is you can see that we actually have VRF'd this physical interface out. We also do some other additional ties. Again, we're not going to get into VRFs, RTs, and RDs. What we're going to do is follow the label to try to figure out how we actually swap these labels in between Charlie6 and Charlie7. So what we're going to go ahead and do is talk about this. So every time we're actually doing MPLS L3VPNs in an environment that's similar to this one, what we're actually going to find is there's multiple labels. Now, what is MPLS? MPLS is multi-protocol label switching, which is interesting because a lot of people seem to then confuse MPLS with LDP, which is Label Distribution Protocol. So MPLS can really swap and label switch any packets that have labels in them, regardless of who puts them in there. Could be LDP, could be BGP, could be RSVP. So, well, traffic engineering tunnels. So it truly is multi-protocol. So let's go ahead and actually look at this. So if we look here, we actually have one BGP connection that is up between Charlie6 and Charlie17. Admittedly, as you saw already, we have an external BGP connection between Charlie6 and router 1 and between Charlie17 and router 2. For right now, go ahead and put that off to the side. That doesn't actually help us or do anything as far as the labels itself are concerned. We're going to use two protocols, BGP VPN v4 and also LDP, to create the labels that we need to go from one side to the other and let this ping happen. So first and foremost, like I said, we have one iBGP VPN v4 peer connection between Charlie6 and Charlie17. It is between their loopbacks, so we have an iBGP peer between 10.100.100.6 and 10.100.100.17. This BGP VPN v4 peer connection will be used to exchange inner VPN labels. We'll see that. Then what's going to happen is, of course, we're also going to run OSPF between Charlie6 and Charlie7, Charlie7 and Charlie16, Charlie16 and Charlie17. We like doing that so that our IGPs actually work and so that Charlie6's loopback can BGP peer with Charlie17's loopback. The OSPF in and of itself at this point in time is not going to be actually doing label distribution propagation. So now we get to LDP, which is another protocol, Label Distribution Protocol. It is actually going to run between Charlie6 and Charlie7, between Charlie7 and Charlie16, and between Charlie16 and Charlie17, and it's going to exchange what I'm going to refer to in MPLS L3VPN terms, outer labels. Now, the LDP routers themselves, so the LDP, the Label Distribution Protocol, doesn't view them as inner labels or outer labels, they're just labels. I'm just saying inner label and outer label so that you can understand from an MPLS L3VPN perspective which protocol actually created which label, the inner label or the outer label. Because for MPLS L3VPN to get across this network, an ICMP echo from R1 to Charlie6 and out, when it goes out of Charlie6, is going to have two labels. Two different protocols were used to do those labels. So here we go. What we're going to do is, the way that I learn a lot about different protocols is I actually use Wireshark. I am a huge fan of Wireshark. So what we're going to do is we're going to see that I have an eBGP relationship, as I mentioned over here, and then BGP Autonomous System 100 in the middle. And again, we have a BGP VPN v4 peer connection between Charlie6 and Charlie17. What I did prior to this video was actually go ahead and put a sniffer trace between Charlie6 and Charlie7. I actually have them on a switch network and I'm spanning a port. Then I'm going to shut down, I already shut down Charlie6's physical interface to that switch that's in the middle. When I no shut, I'm actually going to capture everything. I'm going to capture the OSPF coming up between Charlie6 and Charlie7. I'm going to capture the CDP between Charlie6 and Charlie7. I'm going to capture the LDP neighbor coming up between Charlie6 and Charlie7. I'm also going to capture the BGP VPN v4 connection going up between Charlie6 and Charlie17. And on top of that, I'm going to capture that ping that you saw from R1 to R2. Are you ready? So here's the sniffer trace of everything that happened. So if I go ahead and type up here BGP and I hit enter, what we'll actually see is all of the BGP messages between Charlie6 and Charlie17. You'll actually have this PCAP at your disposal. I will have a link in the YouTube below, pointing to my website that will have a link on Dropbox for the PDF of all these diagrams as well as the PCAP file. So if we go to line 81, because I happen to already know that it's line 81, and we come down here to the path updates, and we go right here to this one. So this is the network reachability. And what we see right here is that 10.100.100.17, which is Charlie17, is sending via BGP VPN v4 to Charlie6 that Charlie17 can reach 10.100.100.2. And if Charlie6 would like to get there, it should send a tag of 20. So what we see then is we actually see exactly what I said here. In line 81 of the sniffer trace, you can find Charlie17 telling Charlie6 that if Charlie6 would like to get to this VPN v4, customer A environment, that Charlie6 can go ahead and come to it, and it needs a tag of 20. So let me ask you a question. Charlie6 will then go ahead and put in its label forwarding table this information. So let's now say that a ping comes in from R1, and R1 sends a ping to 10.100.100.2. Should Charlie6 then take the label 20 and then just kind of sort of send it out in the general direction of Charlie17? Here's the problem. Charlie17 said, this is the label that you need to send so that once it actually gets to me, I can know to send it out to R2. But Charlie17 told Charlie6 about this label. Charlie7 didn't. I don't have a way to, when I send it out, if I send it out with a label of 20 on it, Charlie7 has no idea what that is. In fact, Charlie7 might have even used label 20 for something else towards Charlie6. The labels are independent, okay? So what we need to do is actually find a label that lets us get the label 20 to 10.100.100.17. Remember, 10.100.100.17 is the one who told us use label 20. It is the only one that knows what label 20 is used for. So now we need a label that actually gets us to 10.100.100.17. It gets us to the destination where label 20 will make sense to it. So the inner label is the green one. From an MPLS L3VPN perspective, the inner label for us is the green one. It was done via BGP VPN v4. That is also the VPN label as far as our specific environment is concerned. Now what we need is a second label that we can then label swap between us to get to where that label 20 makes sense. Now we switch to the other one. What we're specifically looking at is we're looking at, in the sniffer trace, the label that Charlie7 is sending to Charlie6, because Charlie6 is going to say, as we see in the arrow right down here, it's going to say via LDP, via the label distribution protocol, via the LDP neighbor that Charlie7 has with Charlie6. It's going to say that I, 10.100.100.7, can get to 10.100.100.17, and you, Charlie6, should use tag 23 to get there. Let's look in the sniffer trace. So if we go to the sniffer trace, and instead of saying BGP, we say we want LDP, then here we go. So we have the hello messages, we have the peer coming up, and then if we go to line 59, and if we actually go to the second from the bottom, third from the bottom, because obviously I've already looked at these. Charlie7 sent the label. It says it can get to 10.100.100.17 that Charlie7 can, and that if Charlie6 wants to use Charlie7 to get to 17, Charlie6 should use the label that Charlie7 is advertising to it and assigning it, which is actually 17. Now if you notice, that's a hex 17. Hex 17 will become decimal 23. Now let's go ahead and go back over to our PowerPoint. So again, as we saw, now that was actually in line 59 of the Sniffer trace. Charlie7 is advertising and saying, Charlie6, if you want to get to the loopback IP address of Charlie17, come out to me and use a tag of 23. So what's actually going to happen is Charlie6 is going to go ahead and take both sets of this information, the BGP VPN v4 information it got from Charlie17, which says that 17 says that it can help you get there, use a tag of 20. That will be our inner label. Then we need another label that actually gets us to the one who told us to use the inner label. And Charlie7, we noticed in line 59 of the Sniffer trace, said to use tag 23. So now we see we're supposed to put a 23 and a 20 in. Now let's see if we can actually find that in Charlie6. So let's go to Charlie6. And I actually have some commands already in here. So I'm going to do a show IP BGP VPN v4. And it's actually a VRF. Customer A, and I'm going to specifically ask for 10.100.100.2, and what we're going to see is we're going to see that in Charlie6, 10.100.100.2, which is over here, is being given via BGP VPN v4 by Charlie17, which is a few hops away, and we are told that the label that we're supposed to send to it is a 20. Now, actually, a command that I really like, which I just did so that I don't have to mess it up, is I like show IP Ceph VRF customer A. So what we're actually doing is we're saying, tell me about the Ceph forwarding table, right? Because we're not going to do these lookups all the time. So what we actually have, and this is the recursion that I was telling you about, and I really like this a great deal. So the BGP VPN, Charlie17 told us to use 20. Okay, so that is the 20 that's right here. And then we have to do a recursion because in order to get to where it makes sense, we have to get to 17. And so that's going to be a 23. So we're actually going to go ahead and we're going to send it out, and it's going to be a 20 and a 23. Now, what's going to happen when we actually send this out? So we send it out with a 23 and a 20. Then what? Then it goes to Charlie7. So when it goes to Charlie7, if we look at the label forwarding table there, the multi-protocol label swapping forwarding table over on Charlie7, what we're looking for is if there is an incoming label somewhere from 23. Charlie7 was the one who told people about it. So let's go to Charlie7 and do a show MPLS forwarding. And what we see is if a 23 comes in, what Charlie7 is instructed to do is swap the labels. Take 23 off, put an outgoing label on of 29, and then send it out gigabit 003. So it's supposed to take the 23, pop it off, push on 29. We call that a swap. So we're supposed to swap 23 for 29 and then send it out. We leave the inner one alone because we're just trying to label swap until we actually get to Charlie17 where the 20 will make sense. So we send it out, we swap it, the 23 for 29, and we send it to Charlie16. Now, before we get to Charlie16, what I want you to understand is I really want you to think about this first, because Charlie16 is going to be a whole new thing. By default, what will actually happen is Charlie16 will be aware of the fact that it is what is referred to as the penultimate hop. The penultimate hop. I know, strange word, okay? But it is the router right before the router that this is going to end at. So there is called penultimate hop popping. What that means is that instead of doing a swap, we're actually going to do a pop and forward it on. That's actually the reason why I have 4 routers here, to really, really help you see what normally happens with the swapping in between, because it's a little bit confusing when you're new to this. Charlie16 is going to go ahead and pop it off. So what's actually going to happen is we're going to go to Charlie16, and Charlie16 knows that it is the router right before the end. It is the router right before 17. And so it's going to actually say, if incoming label is 29, pop that label off and then send it out gigabit 002. It will look like this because the label distribution protocol intelligence has already figured out that Charlie17 is the next hop. So as soon as I send it out this wire, I don't need this blue one anymore, because I'm getting to the place where the green's going to make sense. Again, this is called penultimate hop popping. Let's look at what Charlie16 looks like. Show MPLS. So what we're doing is, what's supposed to happen with 29? 29 comes in right here, and Charlie16 says pop the label, pop it off, and then send it out gigabit 002. So it sends it out gigabit 002, and it gets to Charlie17 as just this label. Now what's Charlie17 supposed to do with this? He's the ultimate destination of the labels. He's the whole reason why we had all those blue labels, so that 20 could make it to where he was the one who told them. So as you can see, Charlie17 has a connection to R2 via gigabit 000. But if we look, Charlie17 does not have an MPLS neighbor connected to gigabit 000. In fact, if we look at interface gigabit 000, MPLS isn't even enabled, which means that I can't send out anything with a label out that interface. So if we actually do an MPLS forwarding here, what we'll see is that the 20, if it comes in as a 20, which we see it came in from Charlie16 as a 20, then it's supposed to go out with no labels. Clear the labels, remove the labels. For us, it was simple. We just pop off the 20. But you have to send it out with no labels. And as you can see, it's actually going to be a VRF instance, and we're going to go out gigabit 000. And if I were to look at the ICMP echo, the ping between R1 and R2 that we captured in the sniffer trace, what should I have there? Let's go look at the sniffer trace. So let's do an ICMP. And what we see is the ICMP going from 10.100.100.1 to 10.100.100.2. Now we know that this is actually in between, and we can see the labels down here. Now, I love Wireshark, it's 23 and 20, but I don't like seeing the labels this way. I much prefer seeing the labels this way. So we're going to go ahead and apply as a column. Now what actually happens when you apply as a column is you see some of them only have 1 label, some of them have 2 labels, and as you can see, this one right here should have 2 labels. It should have 23 as what we're referring to as the outer label, and then 20 as what we're referring to as the inner label. And the reason why it's doing this, I'm going to go ahead and apply another column, is because by default in here, the field occurrence is grabbing both of them. It's saying I don't really care. So what I really want is I want this one to be the first one, and I want this one to be the second one. And if we do that, then what I get what I expect, which is 23 and 20. In fact, what I could do is I could come in here and I could even refer to this as the outer label, and I could refer to this as the inner label. And that's it. A little bit of label swapping fun in the lab with fish. Now, what I hope is that you kind of sort of caught on to all that, because the next YouTube is going to be, I'm going to break something, and we're going to have to find it together. doing a little bit of network detective work. Have a great day. See you soon.